Good day everyone. Today I will be discussing the round-robin CPU scheduling algorithm, which is important concept in operating system. This presentation explains how Robin works, its advantages, and many more. Round-robin is a CPU scheduling algorithm. It is classified as preemptive scheduling algorithm, meaning the CPU can interrupt a running process. Think of it as people taking turns on one computer. Each person gets a short time to use it, and when the time is up, the computer switches to the next person, even if the first one is not finished. The basic idea behind round robin is fairness. The CPU is shared equally among all processes. Each process is given a fixed amount of CPU time called time quantum. The time quantum is the main difference of round-robin among all the CPU scheduling algorithms, and processes are executed in circular order. Now, let's look at how round-robin algorithm works. First, all processes are placed in ready queue. The CPU assigns a fixed time quantum to the first process. If the process finishes within the time quantum, it leaves the system. If not, it is preempted and moved to the back of the queue. The CPU continues this cycle until all processes finished. There are few important rules in round-robin scheduling. First, all processes receive an equal time slice. Second, context switching occurs after each time quantum. Third, order follows a circular queue. Some key terms used in this algorithm include arrival time, burst time, time quantum, waiting time, and the turnaround time. In arrival time, it is when the process enters the ready queue. The burst time is the CPU time needed by this process. The time quantum is a fixed CPU time per process. The waiting time is the total time a process waits. And lastly, the turnaround time is the total time from arrival to completion. Now, let's look at the example. The time quantum is 2 ms or 2 milliseconds. And we have three processes, the P1 to P3. And the burst time of P1 is 5, the burst time of P2 is 3, and the burst time of P3 is 1. And all processes, arrival time is 0. So this slide shows the scheduling order of each process. All processes arrive at the same time and are placed in ready queue. Again, the time quantum is 2 ms or milliseconds, so each process can only run 2 ms or milliseconds per turn. In this table, the P1 runs first. It uses 2 ms of its 5 burst time, leaving 3 ms remaining. The second is the P2. It uses 2 ms of its 3 burst time, leaving 1 ms remaining. Third is the P3. It needs only 1 ms, so it completes immediately. The CPU returns to the next process in the queue. The P1 runs again, uses 2 ms, leaving 1 ms remaining. The second is P2. It runs again and finishes its remaining 1 ms. The last is P1. It completes at final 1 ms. This Gantt chart shows how CPU time is divided from time 0 to 9 milliseconds. Each block represents the exact time a process is using the CPU. The chart starts at time 0. When the first process begins execution, every time the time quantum of 2 milliseconds ends, the CPU switches to the next process, which is why we see a change in the process label. When a process finishes early, like P3, its block is shorter. The chart ends at time 9 milliseconds, which means all processes have completed by that time. So in this slide, we're going to calculate the turnaround time using the formula completion time minus arrival time. So the completion time of P1 is 9, and the completion time of P2 is 8, and the completion time of P3 is 5. And all of these processes have the same arrive time, which is 0. So if we're going to subtract that, that would be 9 minus 0 equals 9. 8 minus 0 equals 8. 5 minus 0 is equals to 5. The next one is waiting time calculation. The formula is waiting time equals turnaround time minus burst time. So the turnaround time of P1 is 9, and the turnaround time of P2 is 8. The turnaround time of P3 is 5. And the burst time of P1 is 5. The burst time of P2 is 3. The burst time of P3 is 1. So if we're going to subtract that, that would be 9 minus 5 is equals to 4. 8 minus 3 is equals to 5. In P3, 5 minus 1 is equals to 4. So in this part, we're going to find the average time of waiting time and the turnaround time. So the first one is waiting time. So in waiting time, we're gonna add the waiting times of all processes and divide by the total number of processes. So in this example, the waiting times are 4, 5, and 4. And the total number is 3. So we're going to add the waiting time of processes. That would be 13. And just gonna add that. And 13 divided by 3 is equals to 4.33 ms. So it's the same for the turnaround time. We add the turnaround times of all processes and divide by the number of processes. So the turnaround times are 9, 8, and 5. Just gonna 10 is equals to, so 9 plus 8 plus 5 is equals to 22. Bring down the 3. So 22 divided by 3 is equals to 7.33 ms. So round robin has several advantages. It provides fair CPU allocation, prevents starvation, and offers good response time. However, it also has limitation. If the time quantum is too small, there can be many context switches. Overall, performance depends heavily on choosing the right time quantum. Round robin is best used in time-sharing system, multi-user operating system, interactive environments, and system where fairness is important. In summary, round robin is a preemptive scheduling algorithm that focuses on fairness. By giving each process a small and equal share of CPU time, it ensures that no process is left waiting too long. This makes it especially useful for systems where quick response is important. Unlike first come first serve, round robin prevents long processes from blocking shorter ones by sharing time in steady turn.